All right. How's everybody today? Okay. All right. Well, I hope everybody's having a good day. We're going to continue our lesson in just a minute. Just a few things. Monday is your second exam. So you're allowed to use a 3x5 index card, whatever you would like to write in order to use during the exam is perfectly fine. It's just got to be a 3x5 index card, front and back. Okay, no additions to it. I did go ahead and a little while ago, because we should be pretty close to wrapping up the lesson today if we don't completely finish it. But with the test coming up on Monday, I did go ahead and post a probability review. Okay, so if you're looking for some extra problems just to get a little some practice before Monday's exam, we have these available right here. And in a separate file, I did go ahead and post those answers. Okay, so welcome to take a look at that. And what is due on Friday? Okay, the homework, so my hope is that early tomorrow we should be able to have this finished. We'll go ahead and start looking at those examples together, probably even have some extra examples to finish out the week. Okay, Jacob and Erica. All right. Oh, it says please send at the end of class. Okay, so I'll go ahead and give them to you now. Yes.
Just gonna let you know today, but Elizabeth, Ethan, Laura, and I will all be leaving at 1:30 tomorrow.
Okay.
We have a swim meet that we're leaving for.
Okay. All right. At 1:30?
Yes.
All right. Just remind me, we'll be good. Erica, there you go. Okay. So let's get started. Oop. Okay. Jacob, if you would turn off that light for me, please, sir. Okay, well, let's see where we ended up yesterday. I know that we got to this portion right here. We started talking about independent. So this is the idea that one event is in no way influenced by another. We had the sentence here that if they are physically independent, then they are mathematically independent. The example that we had was just rolling a pair of dice. Okay, we had, if we know two events are independent, we can find the probability of their intersection by taking the product of their individual probabilities. And then we had the idea that these diagrams we're looking at, if you follow along any particular branch, those are regarded as intersections. Okay, you'd multiply those individual probabilities. Now, if more than one branch gives you the outcome you're looking for, you would add those up. That's what we're referring to as the union. Okay, so I think we were right here on Deborah's problem. Okay, so let's just keep going and see how far we get. Deborah has a 70% chance of winning the 100-meter race and a 60% chance of winning the 200-meter race. Find the probability that she only wins one race. Okay, so we need to see all the possible outcomes that are here. So she could win both. She could win one, or she could win neither. She could unfortunately lose both. So this is another one of those problems where I think a tree diagram is perfect. So let's say for the 100 meter, she's either going to win or she's going to lose. Okay, so what's the percent that she's going to win? We have a 70% chance. So they have data that we don't know about. That's okay. I'm going to go ahead and put the 0.7. So what's the percent that she's going to lose? Okay, 0.3. Now, one thing I want to go ahead and bring up when you're looking at these branches that diverge like this, their sum should always be 1. Okay, should represent 100% every possible outcome that there is. All right. So now we're going to go ahead and branch off into the 200 meter. So if she wins the first one, she could win the second or she could lose the second. This represents the 200 meter. So we know that there's a 60% chance of her winning the 200 meter. So if this is 0.6, there is a 40% chance of her losing that race. Okay, and then I'm going to go ahead and do the same thing for if she loses the first race. She could win. She could lose. So again, we have the same values here, 0.6, 0.4. Oop, put that in the right spot. Okay. Now, it's just like I was talking about a moment ago. For example, if I follow along the first branch, the very top one, okay, I want to know what's the probability that she's going to go ahead and win both races. Well, I have this probability and this one. So I'm going to multiply along this branch. What's 0.7 times 0.6? 0.42. So according to this, there's a 42% chance that she would win both races. Okay. Now let's follow along the next one. She wins the 100 meter, but she loses the 200 meter. So 0.7 times 0.4. 0.28. So 28% chance of that happening. What about if she loses the first, but wins the second? Okay, so 0.18. And finally, we finish up. What, unfortunately, if she loses both of them? Okay, 0.12. Okay. Well, what are we looking for here? Find the probability that she only wins one race. Well, it doesn't specifically say which race, right? So how many branches are going to fit this scenario? Yeah, two. She's either going to win the first race and lose the second, or lose the first and win the second, as long as she gets one. So I'm looking for those outcomes right here. So there was a 28% chance of winning the first race, okay, losing the second. There was an 18% chance of winning the second after losing the first. So this is what I was referring to a moment ago. You see, we multiplied along those branches to get the outcome, but now more than one branch has the outcome that I'm wanting. So I'm going to take the sum of those. 0.28 plus the 0.18, that gives me point what? 0.46. Okay, so I'd say there's a 46% probability that she's only going to win one race. Okay. Is everybody okay with how I got that? Remember, going along the branches, we look at that as an intersection. That's when we multiply. If we have more than one branch that gives me an outcome I want, we total those. We take the sum. That's the union. Okay, well, B, find the probability that she wins both races. Well, that one we actually got at the very beginning. What is it? Yeah, so 42% chance of winning both races. All right, so that's not so bad, is it? Easy? Okay. Okay.
So if the first, this hypothetical,
Mm-hmm.
if she won, had a 90% chance of winning the first one,
Uh-huh.
and then had a 90% chance of winning the second one, that would equal 180. How is that for, like the 1.80?
Mm-hmm.
Because that's not an actual percentage.
You know, I don't know. I never thought about that. That's something I'd have to look up. Let me look into that. I don't know that right off the top of my head. Okay, that's a good question. All right. All right. Let's go ahead and try another one. Carl's not having much luck lately. His car will only start 80% of the time, and his motorbike is only going to start 60% of the time. Draw a tree diagram to illustrate this situation, and then use the tree diagram to determine the chance that both will start, or Carl can only use his car. All right. Yes, ma'am.
The test.
Yeah, 0.9 times 0.9 is 0.81. Yeah, so that was still working. Yeah. What about? Yeah, it's a Wednesday. All right. So who can help me out with this particular problem here? We'll have somebody come on up first and draw the tree diagram, and then we'll see if we can't get somebody up here to help me with the two probability problems. Joey? All right. Okay, Joey's going to help me with the tree diagram. Okay, so this first set of branches is the car. Are you talking about to indicate what happens?
Either it will start or it won't start. So
Mm-hmm.
say what, yes, can I just say yes or no?
Sure, that's a great way to do it. So yes, it starts, or no, it doesn't. So we have an 80% chance it does, 20% it does not. And then from each of those two possibilities, we branch off into the motorbike. Okay, so either yes or no. Good. There you go. That's it. Okay. Now, using this tree diagram, determine the probability that both will start. Okay, so who wants to help me with the two probability questions? Oh, so many hands. Nobody? Okay, well, let's try something different. Joey, who would you like to see answer this question since I won't use a random number generator? We'll start a train. Nobody's making eye contact with Joey. Well, maybe one person.
So the probability that both will start. So you take the positive outcome for the car, which is 0.8, and then the positive. I don't know why you would need both to start, because if your car starts, you need to check the bike.
Well, isn't that normal? If you own both, you would start your car, get out, and see if you can start your motorcycle.
I mean, yeah, it's common practice. But
Yeah.
You're in a rush.
Hey, it's true. I think the bigger question would be, why wouldn't you?
Or if you have a motorcycle, why are you taking a car to work?
Well, also, we keep saying motorcycle, but it says motorbike, which kind of makes me think like a dirt bike. So maybe you don't know. I mean, it says Carl's not having much luck lately. I mean,
But
anyways,
gonna be that's correct. That'll be 0.48.
0.48. So we're looking at 48%. Good.
Chance. And then
What about the chance that Carl can only use his car?
only use his car. So that's gonna say his bike won't start. So if his car does start, but his bike doesn't start, there's a 0.32 that happens.
Okay.
And then his car doesn't start and his motorbike doesn't start. There's a 8 chance. Wait, no, that doesn't.
Now, how many branches will fit this scenario? Can only use his car.
2, 1.
Just the one.
Yeah, just
Because if he's only going to use his car, then that means we need a no from the bike. So you're right.
we'll use car as well.
0.32.
Good point.
Mm-hmm. That's it. That's all there is to it. Right. All right. Good. I thought I'd join in with who was that? Jacob who called? There you go. Okay. We support John here. All right. Questions. Easy, right? None to it. Okay. Well, good. Let's see what else we got. Now, replacement versus without replacement. The probability of an event, a subsequent event occurring, for example, picking a certain colored marble out of a bag, depends upon whether the first choice is returned to the sample space for reselection. If the choice is returned for reselection with replacement, then the probability determination maintains a fixed number of elements in the sample space. If the choice is not returned for reselection without replacement, then the probability determination is based upon the sample space being reduced by one item, and the event has one less possible occurrence. Okay, so let's talk about this one together. So this can best be seen in an example. A box contains 2 red cubes and 4 black cubes. If 2 cubes are selected at random, find the probability that both cubes are red, given that the first cube is replaced before the next cube is selected. Now, do you notice anything about the way this is stated? Does anything kind of jump out at you? Okay. The replaced is important, but I'm looking at something else. Given. Okay. So what does that given imply here? What kind of probability is that? Conditional probability. Now, there is a way that you can go ahead and solve this using conditional probability, the formula that we've talked about over the past couple of days. I'm going to go ahead and save that for just a moment. Let's just go ahead and do it as a tree diagram. All right. So if you go ahead and pull 2 cubes out, okay, the first cube, what are we looking at? Could be what? Could be red or it could be black. Okay. Now, what's the probability of choosing a red first? 2 out of 6, because we've only got 2 red cubes out of the 6 total, right? Well, we know 2/6 is 1/3. Okay. What would be the probability of pulling out a black? 4 out of 6, so that's 2/3. And again, you're going to notice this every time you go to another separation of branches here. 1/3 plus 2/3 does add up to what? 1. Okay, so one of them is going to get chosen. There's a 100% probability of that happening. So depending on which one you chose, then we're going to go ahead and branch off again. So we either have red and black or red and black. But what do we know about the one that we pulled out? Okay, it is, for part A, it is replaced, right? So see, what's going to happen? What's the probability now of pulling out a red? It's still 1/3. I put that red back in, so you still have a 2 out of 6 probability.
We have a lockout right now, so we need to secure the perimeter. There's a threat or hazard outside the building. Against teachers, we have a lockout right now. We're going to secure the perimeter. There's a threat or hazard outside the building. Thank you.
Me too. I gotta go.
But you're safe. I mean,
At least we know how to stop the bleeding.
the glass is half full. You now know how to stop the bleeding. Go. Okay. All right. All right. So hopefully, whatever it is, and Jaylee, we don't know. Maybe it's something small.
It's a crack.
What if it's a cat? What would that cat be doing?
My stomach is crazy. I don't want my cardboard to get
I guess anything's possible. Probably not. Okay. Okay. All right. So we're all safe. We're all safe. Feel math envelop you like a warm blanket. Okay. All right. Okay, so we're filling in this tree diagram right here. Now, after pulling out the red cube, we put it back. So the probability is still 1 out of 3 of pulling out a red. Well, at this point, for these upper branches, I haven't yet pulled out a black yet. So this would also be what right here? 2/3. Again, every time the branches split, that total should be 1. All right, so even if I go along the second branch here where I start 2/3 of pulling out a black cube, well, then I still have a 1/3 probability of pulling out a red. And what do I have now of pulling out a second black if I put it back? Again, still 2/3. It just remains consistent all the way through. Okay. Well, the question says, find the probability that both cubes are red given that the first cube is replaced. Well, according to the diagram, there's only one way that happens. Okay, one branch is going to end up with 2 red cubes. Well, based on what we just did a moment ago with that tree diagram, how am I going to find the probability of pulling out the 2 reds? Yeah, just multiply straight through. So 1/3 times 1/3. So I'm looking at 1/9. Okay. So I'm looking at 1/9. Now, like I said, I'm going to come back in just a second and go over the conditional probability aspect of this. But why don't we go ahead and try B on our own? Okay, now it says find the probability that both cubes are red given that the first cube is not replaced before the second cube is selected. Okay, so that will change the probabilities of the second draws. Okay, so you have to think about you're losing one of those particular colors, but you're also losing one of the 6 in the sample space. That's what the paragraph up here was referring to. So I'll give you about a minute or two. Go ahead and take a look at that. Okay, is everybody about ready? Or do we need a little more time? Okay. Would anybody like to come on up and show me how to fill in the tree diagram? So I'm not asking you to finish up the problem. We just need the probabilities for these selections filled in. Okay. Well, John Henry, you were the last person to come up, right? So now you get to choose. He wants Lucas. And look at the smile on Lucas's face, but we're going to help you. Okay, we're going to help you out. All right. And look at the bright side. If somebody else comes up, you get to choose them. Thanks, sir. Okay. All right, so let's help them out. So we haven't replaced anything yet because we haven't pulled anything out. So what's the probability of just selecting a red cube from the 6? Oh, not 1/6, because how many are there?
Yeah, 1/3.
Okay, so 1/3 because there's 2 red out of the 6 total. Okay, so on that upper branch, we want to go ahead and put 1/3. So if there's a 1/3 probability of pulling out the red, what would be the probability of not pulling out a red or pulling out a black?
4/6, so 2/3.
There you go. And see, that's just another way to kind of look at it. Oh, now remember, we're going for the lower branch, okay? So remember what I used there? I kind of brought the idea back up of a complement. So the probability of pulling out a black now is the same as the probability of not pulling out a red. Is everybody okay with that? You remember how we had 1 minus the complement to get the other portion?
Would you not, in each situation, would you not subtract 1 red from, because...
Oh yeah, but we haven't gotten to the second draw yet. Right now we're just filling in the original. So on the first one, we either have a 1 in 3 probability of pulling out a red, or we have a 2/3, 2 out of 3 probability of pulling out a black. Okay, so let's put that on there. They should. Oh, here we go.
All right, teachers, we're still in a lockout
Oh.
right now, and we're going to be in a hold pattern as well, so we need to keep students inside the classrooms at this time, and we're not going to switch classrooms right now. So again, we're going to be in a hold pattern for a while, and we'll give you more information in a minute. Look at the Navigate Prepared app. Make sure to take attendance. We need to be doing that right now, so we have students counted for. Thank you.
Okay.
Oh, yeah.
Don't panic. Okay, so it was.
No, well, like, in all honesty, the block is probably just like something nearby. Yeah, I'm sure. No, there's like HED agents out there with like pullover masks, and they're just like.
Give me 1 second. I'm sorry, I gotta take a roll on this. Okay. And then who else was there?
Yeah, no, one of like, okay, because there's like a bunch of local friends, but one of them really likes to mess with the ROTC kids, and we've fondly named him Cracker Jack. So Cracker Jack will come by, and he'll go, hey, and we'll be like, all right, cool. Thank you, Cracker Jack. But it's always really funny because he goes to church a lot. Like the church is right over there.
Okay. All right, so I got the attendance submitted for Navigate Prepared. Okay, so Lucas. Now let's say we're now going along the upper branch. We've already pulled out 1 red cube. So what would be the probability of pulling out the second red? In this case, we're not putting it back.
So 1/6, right?
Not 1/6. Because see, there's only 1 red cube left. Now remember, we already had 6, but we pulled 1 out. So there's only 1 red left out of 5 now. There we go.
All right, that makes makes sense.
Okay. So think about this. He went ahead and said that the upper branch there, if he pulls out the first red cube, it's going to be 1 in 3 probability. The probability of the second red would be 1 in 5. See, I'm losing 1 from the number of red cubes and the number in my sample space. Is everybody okay with that?
Are we still on?
We're on part B.
So we're not. So we are replacing.
In part B, we are not replacing. Part A, we replaced, but part B, we're not. So if I have yet to pull out a black cube, what should be the finishing value for that second branch there?
There's 5 in there still.
So there's only 5, but how many black?
There's 4 blacks.
There you go. And that makes sense because what's 1/5 plus 4/5? That's your 1. Remember, it should always be adding up to 1. Okay. So now let's do the same thing along the bottom. So we pulled out 1 black, so we know that there's only 5 left. So what's the probability of pulling out a red now for the third branch? It will be 2/5. Very good. That's it. And now what would be the probability of pulling out the second black? Oh, not 4/5. Now see, that was the first draw if we got a black. Now think about it this way. You've got on the third branch right here a 2/5 probability of pulling out a red. So 2/5 plus what? 3/5 would give me the one that I'm looking for. There we go. Perfect. Okay, nice. Okay. So here's the thing. Is everybody okay where I got these ratios from? Where Lucas got those? Okay, because if you are not replacing that particular item, you're not only losing 1 item from your favorable lot, but you're also losing 1 from the overall sample space. That's why we had to subtract the 1 from the 6 and the 1 from both the 2 and the 4. Is everybody okay with that? Okay. Well, now we have the tree diagram. Okay, so what's the probability that they're both red given that the first cube is not replaced? All right, well, there's 4 outcomes. Well, there's only 1 where they're both going to be red. So how am I going to figure out that probability? Yeah, just multiply through. Remember, this is the intersection. So 1/3 times 1/5, that's going to give me a 1 in 15 probability of getting 2 reds if that first one is not replaced. Okay, so it makes it a little more difficult to pull out the 2 reds if you don't replace it. Because remember, the first time around, it was only a 1 in 9 if you did replace it. Slightly better. Everybody's okay? Okay. Now, I'm going to go ahead and do one of these. Let's do part A when it comes to the conditional probability. This is one thing we were talking about over the past couple of days. Remember, conditional probability is finding...
All right, guys, pardon the interruption. The threat outside the building is over now.
Woohoo!
Lockout has been removed, the hold is removed, so we're back to normal activity as usual. Thank you.
Jaylee has her open period. Yay!
They took away my open period.
I don't know. Maybe it's like the government. We'll just never know.
Police nearby.
Oh, there was police nearby?
Yeah.
Remember,
That's what
I think it's
Mr. Young
check
said.
involved.
I don't know how to respond to that. Okay, well, let's go ahead and finish it up. So I'll go ahead and write out the formula, and then I'll go ahead and fill it in with what we have here. So let me go ahead. So the probability of A given B equals the probability of A intersecting B divided by the probability of what? Was it probability of A or B? Ella, what do you think? B. It's always the probability of what's given. Okay, given this event, so that's what I'm going to go ahead and divide by the probability of. Now, in this case, we're looking for the probability of getting 2 red cubes given that the first cube is replaced. All right, so the probability of 2 red given that the first is replaced. All right, well, let's go ahead and apply this to the formula that we just looked at. And again, you'll see why I didn't bother to go ahead and use this on that, even though technically you could use it as a conditional probability. But this will be the probability of 2 red intersecting the first replaced, okay, divided by the probability of what? The first replaced. Okay. Remember, you're always going to divide by the probability of what's given. Well, you see from the diagram, what's the intersection of getting 2 red if the first is replaced? Oh, not 115. Now, that's part B. We're on part A. 1/9. Remember, this was the only branch that ended up where we had 2 red. And remember, if you follow along one branch, I said that's starts with a I. That's an intersection. So this top probability right here is 1/9 over. Now, what's the probability that the first was replaced? Was the first one replaced? So what's that probability? 1. It was replaced, so there's a 100% chance of that happening. What's 1/9 divided by 1? 1/9. See, that's why I decided to go ahead and present this using a tree diagram, because it just makes more sense to me than actually just kind of forcing that conditional probability. It also kind of gives you the idea that even if you recognize it as conditional probability, you don't necessarily have to use that formula in order to get it. Okay. Is everybody okay with that? Anybody having a hard time? Anybody confused? Okay. Math saw us through that crisis. Yay. Whatever the crisis was. Probably. Mm-hmm. Okay. Jacob, you looked it up on your phone?
No, Mr. Young sent an email.
Oh, he did?
And a text message to my mom.
Oh, but he didn't say what it was?
He just said it was a police
Activity.
Police activity. Maybe there was a burglary, or maybe one of the businesses got robbed, or...
Maybe an old person saw a bird and scared them.
There's been a lot of like drug.
What's with you and old people?
Hey, it's because I think the root of my dislike of old people is that whenever I take my dogs off the leash at the park, they call the cops. I know my neighborhood can call them by name.
Old people suck.
Yeah.
But
No,
you're going to be old one day.
But I won't be that cranky.
Yeah, I'll be old one day, but I won't suck.
they treat the park like it's their front yard.
Yeah, like we. Okay, we.
Well,
No, like.
well, I mean, there is a reason. I mean, your dog may be trained, to obey your orders, but when it comes down to it, it is an animal. So it is possible if you interact with another animal or another person, the dog could react differently than what you see. I mean, I think that's just the reason for the policy.
But.
Like when I take my dog to the park, I have to put her on a leash, because otherwise, pew, that dog's gone. And then you see me trying to run after her, and it's not funny. It's not funny.
Yeah, they also complain so much about people setting up their hammocks at the park that they installed hammock poles.
Really?
Yes.
Now, I don't see a problem with that. That'd be pretty cool.
No, it's against city ordinance. That's the only problem with old poles have.
So maybe when you get older, you can change that.
Maybe.
Maybe.
Or
Interesting. Whose side are you on, Mr. West?
Well, as an old person, I mean, oh, thanks.
We don't categorize you.
you're anywhere from jovial to
Anywhere from what?
You're anywhere from jovial to not old.
Nice word, son.
Jovial to not old. How do you measure jovial?
Joviality.
Jovialness.
Elasticity of cheeks.
Okay.
Kind of sounds like we're skirting on calling me fat.
No.
All right. Math. Okay, math. All right, 159. Bag contains 5 white balls and 4 red balls. 2 balls are selected in such a way that the first ball drawn is not replaced before the next ball drawn. Find the probability of selecting exactly 1 white ball. Okay. Now, I'm going to go ahead and set up the tree diagram. All right, let's see if we can get somebody up here to fill it in and help me determine the probability of choosing a white ball. All right, so what 2 colors do we have? White and red. Okay, so white and red. All right, so we're going to do the same thing as we did in the previous examples. Emma, what's the probability of choosing a white ball?
5 out of 9.
5/9. 5 white balls out of the 9 total, so 5/9. So that means the probability of choosing a red ball is 4/9. Okay, 5/9 plus 4/9 again equals that 1. Okay, so regardless of which one I choose, we can now choose a second one, either white or red. But what's happening here? Is it replaced or is it not replaced? It is not replaced. Okay, so Elizabeth, what? You always sound so happy when I call on you. What's the probability of choosing a second white ball if I've already chosen one? 1/2. Because we've already chosen one white ball, right? So how many are there left? 4 out of 8. So we don't have 9 anymore. We already chose 1. So the sample set is decreasing. Is everybody okay with that? Okay. So what is the probability of choosing a red ball? Yeah, because there's only 4 red out of the 8 that are left. So it's also 1/2. And again, 1/2 plus 1/2, there's your 1. Okay. So now if I chose a red, okay, who haven't I talked to today? Sarah Beth. What's the probability of choosing a white if I've already chosen a red? 5/8. Because there are still the original 5 white balls, but out of 8 total now. And now we don't even really need to think about the probability of the second red. 5/8 plus what would give me 1? Yeah, 3/8. All right. Okay. Any questions on how I created the diagram? All right. Now, what are we looking for? Okay. Probability of selecting exactly 1 white ball. So this diagram is going to help me out. Can anybody come show me? In fact, who was it? Lucas? Who would you like to see solve this last problem? Really? Well, you can't pick Lucas again. He already went. Jan. You know what? I don't think Jan's ever been up to the board. This is awesome. Maybe we should do this more often. All right. Jan. Okay, so we got the tree diagram. So we have to ask ourselves this question: how many of those 4 branches are going to result in us getting just 1 white ball? 2. Okay, which 2? Okay, so there's 1 right there. Okay, so let's go with the top one that you marked, where the first one is white and the second one is red. How would I find the overall probability of getting that branch? There you go. Because remember we said that the branches are intersections, right? So 5/9 times 1/2. So that's going to give me 5/18. Okay. So 5/18 for that top branch, or I should say the second one. Now, what's the probability for first choosing a red and then getting a white? 4/9 times 5/8. So this is going to be 20 70 seconds. Okay. But now there are 2 different branches that end up with us getting a white ball. What do I do with these? We have to add them up. Okay, remember that's the union. The branches themselves are the intersection where we multiply. The end result, that's the union. So all we need to do is figure out, okay, what's 5/18 times, or should we times, plus 2070 seconds. 2070 seconds, let's reduce that. Maybe we'll get a better denominator. In fact, what would that be? 5/18. So what's a 5/18 plus 5/18? Okay, here's what? 10/18. But what's 10/18? 5/9. Good job, Jan. That's it. How we doing? Anybody having problems? Okay. How are we feeling going into the test Monday?
What's all in the test?
Probability. That's it.
Oh, that's it? Oh,
That's it.
yeah, we're good.
We're good? Now remember, we still have 2 days of practice. Most likely on Friday, we'll go ahead, talk about the problems on the homework, Maybe even start tomorrow and then just turn it in at the end. Okay. All right, good.